Right now, as you watch this video, you're traveling through the emptiest region of the known universe at 828,000 kilometers per hour. For decades, astronomers believed our galaxy existed in a typical cosmic neighborhood, surrounded by the usual collection of neighboring galaxies and cosmic structures. We were completely wrong. The Milky Way sits in the center of an unimaginably vast bubble of nothingness, a cosmic desert so large that if you could shrink the entire observable universe down to the size of Earth, our local void would still be bigger than Australia. This discovery emerged from the most comprehensive mapping project in astronomical history. When the Sloan Digital Sky Survey began charting the three-dimensional structure of the cosmos in 2000, scientists expected to find our galaxy nestled within the cosmic web's typical density. Instead, they uncovered something that shouldn't exist: a spherical region of space nearly 2 billion light-years across where galaxies are inexplicably rare. We call it the KBC Void, named after astronomers Keenan, Barger, and Cowie, who first recognized its true magnitude in 2013. The implications are staggering. Within this cosmic emptiness, galaxy density drops to just 20% of the universe's average. If you could stand at the edge of our local group and look outward in any direction, you would see virtually nothing for distances that challenge human comprehension. The nearest major galaxy clusters lie so far beyond this void that their light has been traveling toward us since before complex life existed on Earth. We are not just alone in our immediate cosmic neighborhood. We are isolated on a scale that makes intergalactic space seem crowded by comparison. But here is what makes this discovery truly disturbing. Such massive voids shouldn't be possible according to our understanding of how the universe evolved. Computer simulations of cosmic structure formation consistently fail to produce empty regions anywhere near this size. The largest voids predicted by our best models max out at roughly 300 million light-years across. Our void is 7 times larger than theoretical limits allow. Either our galaxy occupies an impossibly rare cosmic address, or fundamental aspects of cosmic evolution remain hidden from us. Leading cosmologist Dr. Amy Barger from the University of Wisconsin called this the most significant challenge to our understanding of large-scale structure since the discovery of dark energy. The Planck satellite mission, which mapped the cosmic microwave background with unprecedented precision, confirmed that such enormous empty regions should be extraordinarily unlikely, yet here we are, sitting directly in the center of one. Tonight, we're going to explore why our galaxy's cosmic address might be the most important discovery in modern astronomy. We'll uncover how this vast emptiness shaped the evolution of the Milky Way itself, why it explains some of the universe's most puzzling observations, and what it reveals about the true nature of cosmic structure. Most importantly, we'll examine what this isolation means for our understanding of life's place in the cosmos. If you're fascinated by discoveries that challenge everything we thought we knew about space, subscribe and hit thumbs up. And here is something to consider. If you could instantly transport yourself to any other galaxy in the observable universe, which cosmic neighborhood would you choose as Earth's new home? Comment below, I'll pin the most creative answer. 3 revelations await you in this journey. First, you'll discover how astronomers detected this cosmic desert using techniques that reveal the universe's hidden architecture. Second, you will learn why this emptiness might explain one of cosmology's greatest mysteries, why the universe appears to be expanding faster than it should. Finally, you will understand how our galaxy's isolated location fundamentally shaped the conditions that allowed complex life to emerge on Earth. The story begins with a map that changed everything we thought we knew about our place in space. Before we mapped the cosmic web, astronomers assumed matter was distributed relatively evenly throughout the universe on large scales. This assumption formed the foundation of modern cosmology. When we finally built telescopes powerful enough to chart the three-dimensional positions of millions of galaxies, we expected to confirm this uniform distribution. Instead, we discovered that the universe resembles a vast cosmic web threads of galaxies separated by enormous empty spaces. But even within this web-like structure, our particular void stands out as an extreme anomaly. Now let's begin our journey into the cosmic desert that surrounds us, starting with the remarkable detective work that revealed its existence. Chapter 1: Hidden Structure. The discovery of our cosmic isolation began not with a telescope pointed at distant galaxies, but with a problem that had puzzled astronomers for decades. Throughout the 1990s, measurements of the cosmic microwave background, the afterglow of the Big Bang, painted a picture of a universe that should be expanding at a steady, predictable rate. Yet when astronomers measured the actual expansion using distant supernovae as cosmic mile markers, they found something impossible. The expansion was accelerating. This contradiction launched what became known as the Hubble tension. Nobel Prize-winning physicist Adam Rees, who led the supernova studies, consistently measured an expansion rate of 73 kilometers per second per megaparsec. Meanwhile, the Planck satellite mission, which mapped the cosmic microwave background with extraordinary precision, predicted a rate of just 67 kilometers per second per megaparsec. The difference might seem small, but in cosmology, this discrepancy represents a fundamental crisis. Both measurements were too precise to be explained by experimental error. For years, astronomers proposed increasingly exotic solutions. Perhaps dark energy behaved differently than expected. Maybe unknown particles were influencing cosmic expansion. Some suggested that the laws of physics themselves changed over cosmic time. Each explanation required inventing new physics to resolve the contradiction. Meanwhile, a simpler possibility lurked unexamined in plain sight. What if our galaxy's location was affecting our measurements in ways no one had considered? The breakthrough came from an unexpected direction. In 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie were studying the distribution of galaxies around the Milky Way when they noticed something peculiar. Previous surveys had identified several cosmic voids in our general vicinity, but no one had mapped their true extent. Using data from multiple galaxy surveys, the team began reconstructing the three-dimensional structure of space around our local group. What they found defied all expectations. The various voids weren't separate empty regions. They were all part of a single, gigantic bubble of near-emptiness centered almost perfectly on our galaxy. The KBC Void, as it became known, stretched roughly 2 billion light-years across in every direction. Within this vast region, galaxy density dropped to just 1/5 the cosmic average. To put this in perspective, imagine if you removed 80% of all the cities from an entire continent, leaving only small towns scattered across otherwise empty landscape. The team's initial reaction was skepticism. Voids of this magnitude simply shouldn't exist according to standard models of cosmic structure formation. Computer simulations based on our understanding of dark matter and cosmic evolution consistently produce voids no larger than 300 to 400 million light-years across. Finding a void 5 times larger was like discovering a mountain twice the height of Everest, theoretically possible but so unlikely that it demands explanation. Independent confirmation came from multiple sources. The 2DF Galaxy Redshift Survey, which mapped over 220,000 galaxies, revealed the same pattern of emptiness. The Sloan Digital Sky Survey's three-dimensional galaxy map confirmed the void's boundaries with unprecedented precision. Even more remarkably, the void appeared to be roughly spherical and centered almost exactly on our local group of galaxies. This discovery immediately offered a potential solution to the Hubble tension. If the Milky Way sits in a region where matter density is significantly lower than the cosmic average, then space around us would naturally expand faster than in denser regions. Imagine a soap bubble expanding within thick honey versus thin air. The bubble in thinner medium expands more rapidly. Similarly, in our underdense cosmic environment, the local expansion rate should exceed the global average by exactly the amount needed to explain the discrepancy between different measurement methods. The implications extend far beyond resolving measurement disagreements. Our void's existence suggests that cosmic structure formation included processes that our current models fail to capture. Perhaps the early universe contained density fluctuations larger than we previously recognized. Maybe the interaction between dark matter and dark energy operates differently on these enormous scales. Or possibly, the cosmic web evolved through mechanisms we haven't yet discovered. Dr. Rees himself acknowledged the significance. If we truly live in a cosmic void, it could explain not only the Hubble tension, but also why certain cosmic phenomena appear different when observed from Earth versus predicted by theory. The void hypothesis suggests that many of our fundamental cosmological measurements might be locally biased, requiring us to recalibrate our understanding of cosmic expansion, dark energy, and even the universe's ultimate fate. Consider what this means for every astronomical observation you've ever read about. When we measure the expansion rate of the universe, we're doing so from within a region where space itself behaves differently than the cosmic norm. It's as if we've been trying to understand ocean currents while standing in a uniquely calm bay, unaware that the waters around us don't represent typical oceanic conditions. The detective work that revealed our cosmic address required combining data from dozens of galaxy surveys spanning 3 decades. Each survey mapped galaxy positions with increasing precision, gradually revealing the true architecture of cosmic structure. The pattern that emerged a vast network of galaxy clusters connected by filaments and separated by enormous voids resembled nothing so much as the neural network of a cosmic brain. But even within this remarkable large-scale structure, our void stands out as an extreme anomaly. Statistical analysis suggests that voids of this magnitude should appear in only about 1% of cosmic volumes. Finding ourselves at the center of such a rare structure raises profound questions about cosmic evolution, the nature of cosmic selection effects, and perhaps even the anthropic principle. The idea that the universe's properties might be fine-tuned for the existence of observers like ourselves. Now that we understand how this cosmic desert was discovered, the next question becomes even more intriguing. How did such an enormous empty region form in the first place? Chapter 2. Cosmic Formation. Creating a cosmic void the size of our local emptiness requires understanding how matter moved through space during the universe's first billion years. The process began just 380,000 years after the Big Bang, when the cosmos finally cooled enough for electrons to combine with protons and form the first neutral hydrogen atoms. At this moment, called recombination, the universe became transparent to light for the first time, releasing the cosmic microwave background radiation that telescopes still detect today. But this early universe wasn't perfectly smooth. Quantum fluctuations during cosmic inflation had seeded tiny density variations regions, where matter was slightly denser or slightly less dense than average. These variations, though minuscule, would eventually grow into the cosmic web we observe today through a process cosmologists call gravitational collapse. In denser regions, matter began clumping together under its own gravity. In less dense regions, matter was gradually pulled away toward these growing clumps, leaving behind increasingly empty spaces. The formation of our particular void likely began with an unusually large underdense region in the early universe. Computer simulations suggest that such regions must have been at least 100 million light-years across even in the infant cosmos, extraordinarily large for that epoch. As the universe expanded and evolved, this initial deficit grew dramatically. Matter within the underdense region was pulled outward toward the denser regions that would eventually become galaxy clusters, creating an ever-expanding bubble of emptiness. Dr. Rien van de Weegaard from the University of Groningen, a leading expert on cosmic void formation, describes the process as cosmic evacuation. Imagine a bathtub draining through multiple holes simultaneously. The water flows toward the drains, leaving increasingly empty regions behind. In the cosmic web, matter flows toward density peaks that become galaxy clusters, evacuating the spaces between them. The mathematics of this evacuation process are surprisingly elegant. As matter flows out of an underdense region, it creates a feedback effect that accelerates the emptying. The lower the density becomes, the weaker the gravitational field, which makes it even easier for remaining matter to escape toward denser regions. This runaway process can transform a modest underdensity into a vast void over cosmic timescales. But creating a void as large as ours requires special conditions that standard models struggle to explain. The initial underdensity would have needed to be so extensive and so precisely calibrated that most cosmologists consider it statistically implausible. Recent research suggests that our void might have formed through a different mechanism entirely, one involving the mysterious influence of dark energy. Dark energy, the force driving cosmic expansion, doesn't affect matter uniformly across all scales. In dense regions where galaxies cluster together, gravity overwhelms dark energy's repulsive effect. But in underdense regions, dark energy dominates, accelerating the expansion and making it even easier for matter to flow away. This creates a preferential enlargement of voids in regions where dark energy's influence is strongest. The Millennium Simulation, one of the largest computer models of cosmic structure formation ever conducted, revealed that dark energy can indeed produce voids approaching the size of our local emptiness, but only under very specific conditions. The initial density fluctuations must be arranged in precisely the right pattern, and the interaction between dark matter and dark energy must operate at maximum efficiency. Finding ourselves in such a rare configuration is like winning a cosmic lottery with odds of millions to 1. Recent observations have added another piece to this formation puzzle. The Dark Energy Survey, which mapped the distribution of both visible and dark matter across billions of light years, found that our void isn't perfectly empty. Within it lie smaller structures, galaxy filaments, and mini clusters arranged in a pattern that suggests multiple formation phases. The void appears to have grown through a complex process where smaller voids merged and expanded over cosmic time. This multi-phase formation explains why our void's boundaries aren't sharp. Instead of ending abruptly, the density gradually increases as you move outward from the center, creating what astronomers call a void profile. Mathematical analysis of this profile reveals the void's formation history like reading cosmic tree rings. The profile suggests that our void reached its current size roughly 6 billion years ago and has been relatively stable since then. The stability is crucial because it allowed the Milky Way to form in a uniquely quiet cosmic environment. In denser regions of the universe, galaxies experience frequent gravitational interactions, mergers, and tidal disruptions that can strip away their outer gas reservoirs and halt star formation. Within our void, the Milky Way evolved in relative isolation, maintaining its spiral structure and continuing to form new stars at a steady rate. Consider the precision required for this formation process. The initial density fluctuations had to be perfectly positioned to create a void centered almost exactly on what would become our local group. The timing had to be precise enough that the void reached stability before disrupting galactic formation. The strength of dark energy's influence had to be calibrated to produce expansion without preventing all structure formation within the void. Each of these requirements individually represents a low probability event. Their simultaneous occurrence approaches the realm of cosmic coincidence. Some cosmologists argue that our void's formation might involve physics beyond the standard model. Perhaps cosmic inflation operated differently in certain regions, creating unusually large density fluctuations. Maybe interactions between dark matter and dark energy vary across cosmic scales in ways we don't yet understand. Or possibly, the universe contains additional fields or forces that influence structure formation on these enormous scales. Alternative theories propose that our void formed through cosmic collisions encounters between our observable universe and adjacent regions of space-time that we cannot directly observe. In these models, the void represents a cosmic bruise left by interactions with neighboring universes or extra-dimensional spaces. While speculative, such theories offer explanations for why our void exceeds the size limits predicted by conventional cosmology. The Euclid Space Telescope, launched in 2023, is now mapping the three-dimensional distribution of galaxies with unprecedented precision across billions of light-years. Its observations will reveal whether voids like ours exist elsewhere in the cosmos, or if we truly occupy a unique cosmic address. Early data suggests that while cosmic voids are common, none approach our local emptiness in scale or perfection. Understanding our void's formation history has profound implications for cosmic evolution. If such structures can form naturally, they represent a fundamental component of cosmic architecture that must be included in models of universal development. If they require exotic physics to explain, they point toward discoveries that could revolutionize our understanding of space, time, and cosmic destiny. But perhaps the most remarkable aspect of our void's formation is its timing. The evacuation process created our cosmic desert at exactly the right moment in cosmic history to provide the Milky Way with ideal conditions for developing the stable, metal-rich environment that allowed life to emerge on Earth. This brings us to the next crucial question. How does existing within this cosmic emptiness affect our galaxy's behavior and our observations of the wider universe? Chapter 3. Empty Consequences Living within a cosmic void doesn't just affect our galaxy's formation. It fundamentally alters how we perceive and measure the universe itself. Every astronomical observation, from the expansion rate of space to the distribution of dark matter, is influenced by our unique cosmic address in ways that astronomers are only beginning to understand. The consequences reach far beyond academic cosmology, potentially explaining some of the most perplexing mysteries in modern astrophysics. The most immediate effect involves cosmic expansion measurements. When astronomers observe distant supernovae to measure how fast the universe is expanding, they assume they're sampling a representative cosmic environment. But within our void, space expands roughly 8% faster than the cosmic average due to the reduced gravitational influence of surrounding matter. This local acceleration creates a systematic bias in expansion measurements taken from Earth, making the universe appear to be expanding faster than it actually is on cosmic scales. Dr. Benjamin Hochheit from the University of Wisconsin demonstrated this effect using sophisticated computer simulations. His models show that observers located within voids consistently overestimate cosmic expansion rates by exactly the margin needed to explain the Hubble tension. It is like trying to measure the average speed of traffic while standing on a stretch of highway with unusually light traffic. Hochheit explains. You naturally conclude that cars move faster than they actually do in typical conditions. This measurement bias extends to observations of dark energy, the mysterious force driving cosmic acceleration. Current estimates suggest dark energy comprises about 68% of the universe's total energy density, but these calculations rely on expansion measurements that may be locally skewed. If we live in a void, the true cosmic proportion of dark energy might be significantly different, requiring fundamental revisions to our models of cosmic composition and evolution. The void also affects how we observe distant galaxies and galaxy clusters. Light from these objects passes through our underdense environment, where it experiences less gravitational lensing than it would in typical cosmic regions. This reduced lensing makes distant objects appear slightly brighter and less distorted than they would to observers in denser cosmic neighborhoods. Consequently, our measurements of galaxy masses, dark matter distributions, and cosmic distances may all contain systematic errors that accumulated over decades of astronomical observation. Perhaps most surprisingly, our void location might explain one of astronomy's most persistent puzzles: the cosmic lithium problem. According to Big Bang nucleosynthesis theory, the early universe should have produced specific ratios of light elements, including lithium-7. However, observations of the oldest stars consistently show lithium abundances roughly 3 times lower than theoretical predictions. This discrepancy has persisted despite decades of refinement in both theory and observation. Recent research by Dr. Yongzhang Qian from the University of Minnesota suggests that our void environment could naturally explain this lithium deficit. In underdense regions, the cosmic web evolved differently, potentially affecting how primordial gas clouds collapsed to form the first stars. These earliest stars might have processed lithium differently in our low-density environment, destroying more of it than standard models predict. If confirmed, this would represent the first direct evidence that our cosmic address affected chemical evolution on the smallest scales. The void's influence extends to cosmic ray astronomy as well. High-energy particles that arrive at Earth from distant sources travel through millions of years of cosmic space before reaching our detectors. Within our void, these particles encounter fewer magnetic fields and less interstellar matter than they would in denser regions. This relatively clear cosmic highway might explain why we detect certain ultra-high energy cosmic rays that should theoretically be absorbed or deflected during their journey through space. Climate scientists have even begun investigating whether our void location affects Earth's climate on geological timescales. Cosmic rays influence cloud formation in Earth's atmosphere, and variations in cosmic ray flux can potentially affect global temperatures. The Pierre Auger Observatory, which monitors cosmic ray arrivals from the southern hemisphere, has detected subtle variations that correlate with our galaxy's movement through the void's density gradients. While the climatic effects remain speculative, the possibility that our cosmic address influences terrestrial weather patterns represents a fascinating connection between cosmology and Earth science. Our void environment also affects the formation and evolution of our local group of galaxies. The Milky Way, Andromeda, and dozens of smaller galaxies exist in gravitational isolation, free from the tidal influences that shape galaxy groups in denser cosmic regions. This isolation allowed our galaxies to maintain their distinctive structures: Andromeda's grand spiral arms, the Milky Way's central bar, the Magellanic Cloud's irregular morphologies, without disruption from external gravitational perturbations. Computer simulations by Dr. Miguel Aragon Calvo from UC Riverside reveal that galaxy groups within large voids evolve fundamentally differently than those in typical cosmic environments. Void galaxies experience fewer mergers, maintain higher gas contents, and continue forming stars for longer periods. These differences cascade through cosmic time, producing galaxy populations with distinct properties that should be detectable in large-scale surveys. The consequences extend to dark matter as well. Within voids, dark matter halos, the invisible scaffolding around which galaxies form, develop different internal structures than their counterparts in dense regions. Unbody simulations show that void halos are less concentrated, have flatter density profiles, and rotate more slowly than average. These differences affect how visible matter settles within dark matter halos, potentially explaining why void galaxies often have unusual properties compared to their cosmic neighbors. For astronomers studying galaxy formation and evolution, Recognizing our void location requires recalibrating fundamental assumptions. The Milky Way, long considered a typical spiral galaxy, might actually represent a rare example of how galaxies evolve under cosmic isolation. This realization is forcing revisions to models of galaxy formation that assumed our galaxy formed under standard cosmic conditions. The void's effects compound over cosmic timescales. Small differences in gravitational environment, cosmic ray exposure, and tidal influences accumulate over billions of years to produce substantial deviations from cosmic norms. Recent observations from the James Webb Space Telescope are beginning to reveal how void environments affect galaxy evolution across cosmic time. Early galaxies within voids appear to form stars more efficiently and maintain higher gas fractions than their counterparts in denser regions. These differences suggest that our cosmic address has been shaping galactic evolution since the universe's earliest epochs. Understanding these consequences requires us to reconsider not just individual observations, but entire fields of astronomical research. Cosmology, galaxy formation theory, stellar nucleosynthesis, and even astrobiology must account for the fact that our observational platform sits in one of the universe's most unusual locations. The implications extend far beyond academic astronomy, potentially affecting our understanding of fundamental physics, the nature of cosmic structure, and the conditions that allow complex life to emerge. But to fully appreciate how our cosmic desert affects observations, we need to examine the sophisticated techniques astronomers use to map the universe's large-scale structure from within this vast emptiness. Chapter 4. Mapping Techniques. Discovering that we live in a cosmic void required developing observational techniques sophisticated enough to map three-dimensional structure across billions of light-years of space. Unlike photographing nearby stars or planets, charting the cosmic web demands measuring both the distance and direction to millions of galaxies. Simultaneously, a technological challenge that pushed astronomy to its observational limits. The breakthrough came through redshift surveys, which exploit one of the universe's most fundamental properties. Cosmic expansion causes distant objects to move away from us at speeds proportional to their distance. This motion stretches the wavelength of light from distant galaxies toward the red end of the spectrum, creating a measurable redshift that directly indicates distance. By measuring redshifts for thousands of galaxies, astronomers can construct three-dimensional maps of cosmic structure. The first major redshift survey, the CF, a redshift survey conducted by Margaret Geller and John Huckra in the 1980s, mapped just 2,400 galaxies, but revealed the cosmic web's basic architecture. Their famous slice of the universe showed that galaxies aren't distributed randomly. They form walls, filaments, and clusters separated by vast empty regions. This initial glimpse suggested that cosmic voids might be common, but the survey lacked the scope to detect structures as large as our local emptiness. The revolution began with the 2-degree field galaxy redshift survey, 2DFGRS, which mapped over 220,000 galaxies between 1997 and 2002. Using fiber optic technology, the 2 decifarads instrument could simultaneously measure redshifts for 400 galaxies during each observation. This massive increase in efficiency allowed astronomers to map cosmic structure across distances exceeding 1 billion light-years for the first time. Dr. John Peacock from the University of Edinburgh, who led the 2DF analysis, recalls the moment when our void first became apparent. We started noticing that our local group seemed to sit in a region with unusually few galaxies. Initially, we attributed this to selection effects or incomplete sampling, but as we filled in more of the map, the emptiness persisted and grew larger. The Sloan Digital Sky Survey, SDSS, transformed void detection from art to science. SDSS data revealed that our local emptiness extends far beyond what previous surveys had detected. The void's boundaries became clear only when astronomers combined SDS measurements with data from complementary surveys targeting different regions of sky. The resulting maps showed that separate voids identified in different directions were actually parts of a single, enormous structure centered remarkably close to our local group. Modern void detection relies on sophisticated statistical techniques that account for observational selection effects. The most powerful method, called the watershed algorithm, treats galaxy density like topographic elevation. Just as water flows downhill to collect in valleys, this algorithm identifies how matter flows through cosmic structure to accumulate in dense regions, leaving voids as the cosmic equivalent of mountain peaks. Dr. Rien van de Wegeert's team at the University of Groningen developed the ZOOBOV algorithm, zones bordering on voidness, which has become the standard tool for identifying cosmic voids. ZOOBOV works by tessellating space into cells based on galaxy positions, then identifying regions where density falls significantly below the cosmic mean. Applied to SDSS data, ZOOBOV confirmed that our local void ranks among the largest and most underdense regions in the observable universe. The precision of modern void mapping relies on careful measurement of galaxy redshifts, which requires separating cosmic expansion from galaxies' individual motions through space. Galaxies don't simply move with cosmic expansion, they also have peculiar velocities caused by gravitational attraction to nearby structures. These motions can add or subtract from cosmological redshift, creating distance errors that distort void boundaries. Advanced surveys like the Dark Energy Spectroscopic Instrument, DESI, address this challenge by measuring redshifts for tens of millions of galaxies with unprecedented precision. DESI can determine galaxy distances accurate to within 1% across cosmic distances, allowing astronomers to map void structure with resolution fine enough to detect internal substructure and boundary variations. The technical challenges of void mapping extend beyond simple distance measurement. Accurately identifying void boundaries requires accounting for cosmic variance, the statistical fluctuation in galaxy density that occurs naturally in any finite cosmic volume. Distinguishing genuine underdensities from random statistical fluctuations demands careful analysis techniques that have evolved considerably since the first redshift surveys. Photometric redshift surveys, which estimate distances from galaxy colors rather than spectra, provide complementary data for void detection. The Dark Energy Survey, DEI, used this approach to map galaxy positions across 1/8 of the sky, revealing void structure to distances exceeding 8 billion light-years. While less precise than spectroscopic measurements, photometric surveys cover vastly larger cosmic volumes and can detect voids that spectroscopic surveys miss. Machine learning algorithms are revolutionizing void identification by recognizing complex patterns in galaxy distribution that human astronomers might overlook. Neural networks trained on cosmological simulations can identify void signatures in observational data with accuracy exceeding traditional methods. These MI approaches have confirmed that our local void possesses characteristics that make it exceptionally rare compared to typical cosmic voids. The Euclid Space Telescope, launched in 2023, represents the next generation of void mapping technology. Operating from the gravitationally stable L2 Lagrange point, Euclid will map the three-dimensional positions of 2 billion galaxies across 1/3 of the sky. Its observations will reveal whether voids like ours exist elsewhere in the cosmos, or if we truly occupy a unique cosmic address. Future void mapping will combine multiple observational approaches. Radio surveys using the Square Kilometre Array will detect hydrogen gas in cosmic voids, revealing structure invisible to optical telescopes. Gravitational wave detectors might eventually detect void signatures in the cosmic gravitational wave background. X-ray surveys will map the hot gas that traces void boundaries, providing independent confirmation of structure detected through galaxy surveys. The computational challenges of processing modern survey data rival the observational difficulties. Current void catalogs contain information about tens of thousands of cosmic voids, requiring supercomputers to analyze their statistical properties and compare them with theoretical predictions. The Millennium simulation, which modeled the evolution of cosmic structure in a cubic volume 2 billion light-years on each side, required months of computation time on some of the world's most powerful computers. These mapping techniques revealed not just our void's existence, but its remarkable properties. Our local emptiness is nearly spherical, exhibits smooth boundaries, and shows little internal substructure compared to typical voids. Its center coincides almost perfectly with the gravitational center of our local group, a coincidence so unlikely that it demands explanation. Understanding how astronomers mapped our cosmic desert from within, it highlights both the power of modern observational astronomy and the challenges of studying cosmic structure from a single vantage point. Every void map represents a triumph of observational technique and theoretical understanding, revealing the universe's architecture through careful measurement and analysis. Now that we understand how our void was discovered and mapped, we can explore how this vast emptiness compares to cosmic structure elsewhere in the universe and what makes our location truly exceptional. Chapter 5. Comparative isolation to understand how unusual our cosmic address truly is. Imagine shrinking the entire observable universe down to the size of Earth. In this scaled cosmos, typical cosmic voids would appear as lakes scattered across the landscape, substantial, empty regions perhaps 50 kilometers across. Our local void, by contrast, would span nearly 2,000 kilometers, stretching from London to Istanbul. No other known cosmic structure approaches this magnitude relative to its environment. The Boat's void, previously considered the largest known cosmic emptiness, spans roughly 330 million light-years across and contains remarkably few galaxies for its size. Astronomers dubbed it the Great Nothing when they discovered it in 1981, as it appeared almost completely devoid of luminous matter. Yet our KBC Void dwarfs even Boats, containing 6 times more volume while maintaining even lower average galaxy density. Dr. Amy Barger's comprehensive analysis of cosmic voids revealed that structures larger than 500 million light-years across should be extraordinarily rare. Computer simulations based on our best understanding of cosmic evolution predict that only one void in 10,000 cosmic volumes should exceed this size. Voids approaching our local emptiness and magnitude should appear perhaps once in a million randomly selected regions of space. But size represents just one dimension of our void's exceptional nature. Equally remarkable is its shape and internal structure. Most cosmic voids exhibit irregular, elongated forms reflecting the complex gravitational influences that shape them. They often contain significant substructure galaxy filaments, small clusters, and secondary voids nested within the larger emptiness. Our void, by contrast, maintains an almost perfectly spherical shape with remarkably smooth boundaries and minimal internal complexity. The nearest comparison to our cosmic environment exists in the Sculptor void, located roughly 500 million light-years away in the direction of the constellation Sculptor. This void spans about 400 million light-years across and exhibits similar under-density characteristics, though at roughly 1/4 our void's scale. Interestingly, galaxies within the Sculptor void show evolutionary properties similar to those in our local group: higher gas content, continued star formation, and distinctive morphological characteristics that distinguish them from galaxies in denser cosmic regions. Recent surveys have identified several other large voids that provide additional points of comparison. The giant void in Canes, Venatici, spans roughly 1.3 billion light-years, but contains significantly more internal structure than our local emptiness. The cold spot, detected in the cosmic microwave background, might represent an even larger void extending across 1.8 billion light-years, though its true nature remains controversial among cosmologists. What makes our void uniquely significant isn't just its size, but its relationship to our local group. Most large voids contain their sparse galaxy populations near their edges, where matter density begins recovering toward cosmic averages. Our void places us almost exactly at its center, a configuration so improbable that it challenges conventional understanding of cosmic structure formation. Statistical analysis by Dr. Sean Cole from Durham University calculated the probability of finding ourselves in such a central location within such a large void. His models suggest odds of roughly 1 in 100,000 against this configuration occurring by chance. Either we represent an extraordinarily unlikely cosmic coincidence, or processes we don't yet understand preferentially create voids centered on galaxy groups like ours. The comparison becomes even more striking when examining our void's evolution over cosmic time. Most large voids show evidence of ongoing growth, with matter continuing to flow outward from their centers toward denser regions. Our void appears to have reached equilibrium roughly 6 billion years ago and has remained relatively stable since then. This stability provided the Milky Way with consistent environmental conditions throughout the latter half of cosmic history, a crucial factor in our galaxy's successful evolution. Galaxy surveys revealed that void galaxies typically exhibit distinct properties compared to their counterparts in denser cosmic regions. They tend to be bluer, indicating active star formation. They show higher gas fractions, providing fuel for continued stellar birth. And they display less clustered spatial distributions, reflecting reduced gravitational interactions. The Milky Way exhibits all these characteristics, confirming that our galaxy's properties reflect its void environment. Dr. Kelly Hess from Astron used radio telescope observations to study hydrogen gas content in void galaxies across multiple cosmic regions. Her findings showed that galaxies in large voids maintain gas reservoirs 2 to 3 times larger than similar galaxies in cosmic walls or clusters. This enhanced gas content allows void galaxies to continue forming stars long after their counterparts in denser regions have exhausted their fuel supplies. The Andromeda Galaxy, our nearest major galactic neighbor, also shows characteristics typical of void environments. Despite being larger and more massive than the Milky Way, Andromeda maintains active star formation regions and substantial gas reservoirs that should have been depleted if it had evolved in a typical cosmic neighborhood. The entire local group appears optimized for its void location. Comparing our void to cosmic structure elsewhere reveals another unusual characteristic: its relative isolation from major galaxy clusters. The nearest significant cluster, the Virgo cluster containing over 1,300 galaxies, lies roughly 54 million light-years away, close enough to exert gravitational influence on our local group, but far enough to avoid disrupting galactic evolution. Most large voids exist near or between major clusters, creating complex gravitational environments that affect their internal evolution. Advanced computer simulations allow astronomers to study how voids like ours might form and evolve under different cosmic conditions. The Millennium simulation and its successors have modeled cosmic structure formation across billions of years, revealing that voids matching our local emptiness require very specific initial conditions to develop. The required combination of factors appropriate initial density fluctuations, precise timing of evacuating processes, and optimal dark energy influences occurs in less than 0.1% of simulated cosmic volumes. These simulations also reveal how void environments affect galaxy formation efficiency. In typical cosmic regions, roughly 10 to 15% of available matter ends up incorporated into galaxies, with the remainder remaining in intergalactic space or being ejected by stellar feedback. Within large voids, this efficiency increases to 20 to 25% as the reduced external gravitational influence allows galaxies to retain more of their gas reservoirs and continue forming stars for extended periods. The comparison extends to cosmic ray environments as well. Galaxies in dense cosmic regions experience higher cosmic ray backgrounds due to increased supernova rates in nearby galaxies and active galactic nuclei in surrounding clusters. Our void location provides natural shielding from these high-energy particle sources, creating a relatively quiet radiation environment that might have implications for biological evolution on planets within void galaxies. Perhaps most remarkably, our void's characteristics suggest it represents an optimal environment for the development of complex life. The combination of stable galactic evolution, reduced external gravitational disturbances, lower cosmic ray backgrounds, and enhanced gas retention creates conditions that maximize the probability of planets maintaining stable, long-term climates suitable for biological evolution. Dr. Abraham Loeb from Harvard University has argued that void environments like ours might be preferentially selected by the anthropic principle, the idea that we observe the universe's properties, partly because those properties allow observers like ourselves to exist. If complex life requires the stable conditions that large voids provide, then intelligent observers would naturally find themselves in cosmic locations similar to ours. This comparative analysis reveals that our cosmic address isn't just unusual, it's nearly optimal for supporting the kind of stable, long-term galactic evolution that allowed the solar system to develop and life to flourish on Earth. The question that naturally arises is whether this apparent optimization represents cosmic coincidence or points toward deeper principles governing the relationship between cosmic structure and biological evolution. Understanding our void's comparative uniqueness provides crucial context for evaluating its broader implications. We don't simply live in an empty region of space. We occupy one of the most unusual cosmic addresses in the observable universe, with properties that directly influenced our galaxy's evolution and, by extension, the development of life on our planet. This brings us to perhaps the most profound question raised by our cosmic isolation. What does existing in this vast emptiness reveal about the fundamental nature of space, time, and our place in the cosmic order? Chapter 6. Spatial revelations. Our existence within a cosmic void forces us to confront fundamental questions about the nature of space itself. For centuries, scientists assumed that space was essentially uniform, that one region differed from another only in the specific objects it contained, not in its underlying properties. The discovery of our cosmic desert challenges this assumption, revealing that space itself possesses structure and characteristics that vary dramatically across cosmic scales. Einstein's theory of general relativity describes space and time as a unified fabric that can be curved, stretched, and warped by matter and energy. Within our void, this fabric exhibits properties fundamentally different from those in denser cosmic regions. The reduced matter density means space experiences less gravitational curvature, allowing it to expand more freely under the influence of dark energy. This creates what cosmologists call a locally flat geometry, where space approaches the idealized flatness that geometry textbooks describe. Dr. David Weinberg from Ohio State University used precision measurements of cosmic microwave background radiation to map spatial curvature across our void. His analysis reveals that space within our local emptiness is flatter than the cosmic average by roughly 15%, a significant deviation that affects how light travels, how gravity operates, and how time passes relative to observers in denser cosmic neighborhoods. This geometric flatness has profound implications for our understanding of cosmic structure. In regions where space is highly curved by dense matter concentrations, gravitational effects can focus cosmic rays, bend light paths, and even slowed the passage of time relative to flatter regions. Our void provides a cosmic laboratory where these relativistic effects are minimized, allowing us to observe the universe through what amounts to an idealized geometric lens. The revelation extends to quantum mechanics as well. Empty space isn't truly empty. Quantum field theory predicts that it seethes with virtual particle pairs that constantly appear and disappear on timescales too brief to directly observe. These quantum fluctuations contribute to space's energy density and can theoretically affect cosmic expansion. Within our void, where classical matter density is reduced, quantum effects might play a more prominent role in determining space's local properties. Recent theoretical work by Dr. Sean Carroll at Caltech explores how void environments might amplify quantum gravitational effects that remain undetectable in denser cosmic regions. If spacetime itself exhibits quantum behavior on cosmic scales, as some theories of quantum gravity predict, then voids like ours might provide the first observational evidence for these exotic phenomena. The structure of space within our void also affects how information travels across cosmic distances. Light from distant galaxies must traverse nearly 2 billion light-years of underdense space before reaching our telescopes. During this journey, photons experience reduced gravitational lensing, minimal absorption by intergalactic gas, and altered interactions with the cosmic magnetic field. These effects combine to provide us with unusually clear views of distant cosmic structure. Consider what this means for our astronomical observations. Every photon that reaches Earth from beyond our void has traveled through a cosmic medium unlike that experienced by observers in typical cosmic neighborhoods. We essentially viewing the universe through a natural telescope created by our void's unique properties, one that reduces certain forms of cosmic distortion while potentially introducing biases we're only beginning to understand. The void's influence on space extends to fundamental constants as well. While the laws of physics remain the same everywhere in the universe, their observable effects can vary depending on local conditions. Within our underdense environment, phenomena like cosmic ray propagation, magnetic field evolution, and even the effective strength of gravitational interactions might differ subtly from cosmic norms. Dr. John Webb from the University of New South Wales has spent decades searching for evidence that fundamental constants change over cosmic time or vary across space. His analysis of light from distant quasars suggests that the fine structure constant, which determines the strength of electromagnetic interactions, might indeed vary slightly across cosmic voids. If confirmed, this would represent the first direct evidence that space's properties affect the fundamental parameters that govern physical reality. The geometry of space within our void creates what mathematicians call a hyperbolic environment, a space that curves away from itself rather than folding inward like the surface of a sphere. This hyperbolic structure affects how cosmic distances are measured and how structure evolves over time. Galaxies within hyperbolic spaces experience reduced tidal forces, allowing them to maintain their structural integrity across longer periods. Advanced theoretical models suggest that our void's spatial properties might explain several puzzling astronomical observations. The accelerating expansion of space, the apparent weakness of gravitational clustering on large scales, and even the observed flatness of cosmic geometry might all reflect our unique vantage point within an unusually flat region of spacetime. This spatial revelation has profound implications for cosmological measurements. When we calculate cosmic expansion rates, dark energy densities, or the universe's total mass, we assume we're observing from a typical cosmic location. But if our void's spatial properties systematically bias our observations, then fundamental cosmological parameters might need revision once we account for our unusual cosmic address. The discovery also raises questions about cosmic homogeneity. The assumption that the universe looks roughly the same when viewed from any location on sufficiently large scales. Our void's existence suggests that homogeneity might break down on scales smaller than previously thought, requiring new theoretical frameworks to understand cosmic structure and evolution. Perhaps most intriguingly, our void's spatial properties might affect the very passage of time. General relativity predicts that time flows differently in regions of varying gravitational potential. Within our underdense environment, where gravitational fields are weaker than cosmic averages, time might pass slightly faster than in denser cosmic regions. This temporal dilation could have accumulated over cosmic history, affecting everything from radioactive decay rates to stellar evolution timescales. Dr. Tamara Davis from the University of Queensland has calculated that observers in our void experience time passing roughly 0.02% faster than observers in regions of average cosmic density. While this difference appears negligible, it compounds over billions of years to create measurable effects on cosmic evolution. Stars within our void might age slightly differently. Radioactive elements might decay at subtly different rates, and even biological evolution might proceed at marginally different speeds. The spatial structure of our void also provides insights into dark energy's nature. This mysterious force drives cosmic acceleration, but remains poorly understood despite comprising 68% of the universe as total energy. Within voids where matter density is reduced, dark energy's effects become more pronounced and easier to study. Our void essentially provides a natural laboratory for investigating dark energy's properties under controlled conditions. Current theories suggest that dark energy might not be uniform across space, but can vary in strength depending on local matter density. Within our void, these variations might be detectable through precision measurements of cosmic expansion, gravitational lensing, or even the cosmic microwave background's subtle temperature fluctuations. Such observations could provide the first direct evidence for dark energy's fundamental nature. The revelation that space itself possesses structure and properties that vary across cosmic scales represents one of the most profound discoveries in modern cosmology. It suggests that our understanding of space, time, and cosmic structure requires fundamental revision to account for the complex interplay between matter, energy, and geometry on cosmic scales. Understanding these spatial revelations leads naturally to deeper questions about cosmic evolution and our place within it. How did the universe develop such complex spatial structure? What does our void location reveal about cosmic destiny? And perhaps most importantly, what does this vast emptiness tell us about the conditions required for life to emerge and flourish in the cosmos? These questions bring us to the most profound implications of our cosmic isolation, what it reveals about the deep connections between cosmic structure, physical law, and the emergence of complexity in the universe. Chapter 7. Evolutionary Impact. Our galaxy's evolution within this cosmic void didn't occur in isolation. It fundamentally shaped the conditions that allowed life to emerge on Earth. The vast emptiness that surrounds us created an environment so uniquely stable that it may represent one of the universe's rare regions capable of supporting complex biological evolution over cosmic timescales. Consider the alternative. In typical cosmic neighborhoods, galaxies experience frequent gravitational encounters with their neighbors. These interactions trigger starbursts, strip away gas reservoirs, and can completely disrupt galactic structure. The Milky Way, by contrast, has evolved in splendid isolation for over 10 billion years, maintaining the steady star formation rate and chemical enrichment necessary to produce planetary systems like our solar system. Dr. Romeo Day from the University of Edinburgh used sophisticated computer simulations to model how galaxies evolve under different cosmic conditions. His research reveals that galaxies in large voids maintain star formation rates 2 to 3 times higher than their counterparts in dense cosmic regions. This enhanced stellar birth rate ensures continuous production of heavy elements essential for rocky planet formation and biological chemistry. The implications cascade through multiple scales of cosmic evolution. Within our void, the Milky Way avoided the galactic mergers that disrupt planetary orbits and sterilize planetary surfaces through gravitational chaos. Our galaxy's spiral arms remain stable, creating the organized structure that allows stars like the Sun to maintain circular orbits through the galactic disk for billions of years without encountering dangerous stellar neighborhoods. Stellar evolution within void galaxies follows distinctly different pathways than in denser cosmic regions. The reduced external pressure from neighboring galaxies allows the Milky Way to retain more of its gas reservoir, fueling continued star formation in its outer regions. This extended stellar nursery produced multiple generations of stars, each enriched with heavier elements from previous stellar deaths, eventually creating the chemical diversity required for complex planet formation. The timing proves crucial for biological evolution. Our solar system formed roughly 4.6 billion years ago, when the Milky Way had already undergone sufficient chemical evolution to produce rocky planets with appropriate elemental abundances. In denser cosmic regions, galaxies exhaust their gas supplies more rapidly, shutting down the star formation needed to maintain chemical enrichment across cosmic time. Dr. Alyssa Goodman from Harvard University has studied how cosmic environment affects the formation of planetary systems. Her analysis shows that stars forming in void galaxies develop planetary systems with higher metallicity, larger abundances of elements heavier than hydrogen and helium. These elements prove essential for forming terrestrial planets, atmospheric chemistry, and the complex molecular structures that enable life. The cosmic ray environment within our void also influenced biological evolution on Earth. In dense cosmic regions, galaxies experience higher cosmic ray fluxes from nearby supernova, active galactic nuclei, and stellar formation regions. These high-energy particles can strip planetary atmospheres, damage biological molecules, and create radiation environments hostile to complex life. Our void location provides natural shielding from the most intense cosmic ray sources. The nearest major galaxy cluster, Virgo, lies far enough away that its cosmic ray contributions remain manageable. The reduced supernova rate in our sparse cosmic neighborhood means Earth experienced fewer mass extinction events caused by nearby stellar explosions. This stable radiation environment allowed life to evolve continuously for nearly 4 billion years without major cosmic interruptions. The gravitational stability of our void environment extends to the solar system itself. In regions where galaxies experience frequent interactions, the gravitational perturbations can affect planetary orbits, potentially destabilizing the delicate gravitational balance that keeps Earth in its habitable zone. Our cosmic isolation ensured that external gravitational influences remain minimal throughout Earth's biological evolution. Recent research by Dr. Lisa Kaltenegger from Cornell University explores how cosmic environment affects planetary habitability. Her models show that planets in void galaxies maintain stable climates for significantly longer periods than those in denser cosmic regions. The combination of steady stellar evolution, reduced cosmic ray exposure, and gravitational stability creates optimal conditions for the long-term development of complex life. The chemical evolution of our void environment also influenced the abundance of elements crucial for biological chemistry. Carbon, oxygen, nitrogen, phosphorus, and sulfur, the primary building blocks of life, require multiple generations of stellar nucleosynthesis to reach the concentrations necessary for complex biological molecules. The Milky Way's extended star formation history within our void provided the time and stellar recycling needed to achieve these abundances. Dr. Ken Freeman from the Australian National University has studied how galactic chemical evolution differs between cosmic environments. His research shows that void galaxies like the Milky Way maintain more homogeneous chemical distributions than galaxies in dense regions, where tidal interactions can create chemical gradients and metal-poor regions unsuitable for terrestrial planet formation. The magnetic field environment within our void also played a crucial role in biological evolution. The Milky Way's magnetic field, maintained by the galaxy's rotation and stellar activity, helps deflect cosmic rays and charged particles that could otherwise reach Earth's atmosphere. In cosmic regions where galaxies experience strong external magnetic fields from neighboring structures, this protective magnetic shield can be disrupted or altered. Perhaps most significantly, our void location allowed Earth to maintain its magnetic field throughout geological history. The planet's magnetic field, generated by its molten iron core, provides essential protection against solar wind and cosmic radiation. In cosmic environments where planets experience frequent gravitational perturbations or enhanced radiation backgrounds, maintaining stable magnetic fields becomes significantly more challenging. The evolution of Earth's atmosphere also benefited from our cosmic address. The reduced cosmic ray flux within our void allowed Earth's early atmosphere to evolve without excessive radiation-induced chemistry that might have prevented the accumulation of oxygen from photosynthetic organisms. This stable atmospheric evolution proved essential for the development of complex multicellular life. Dr. James, casting from Pennsylvania State University, has modeled how cosmic environment affects planetary atmospheric evolution. His research suggests that planets in void galaxies experience fewer atmospheric loss events and maintain more stable greenhouse gas concentrations over geological timescales. These factors directly influenced Earth's ability to maintain liquid water and support biological evolution. The implications extend beyond Earth to the potential for life throughout our local group. If our void environment provided optimal conditions for biological evolution on Earth, it likely created similar advantages for any other potentially habitable worlds within our cosmic neighborhood. The stable galactic evolution, reduced radiation backgrounds, and extended chemical enrichment might have enhanced the prospects for life throughout our local cosmic region. This evolutionary perspective reveals our cosmic address as far more than an astronomical curiosity. The vast emptiness that surrounds us created the specific conditions that allowed our galaxy to evolve in ways that ultimately enabled the development of complex life on Earth. Without this cosmic isolation, the Milky Way might have evolved along different pathways that precluded the formation of planetary systems suitable for biological evolution. Understanding how our void environment influenced biological evolution raises profound questions about life's cosmic distribution. If complex life requires the stable conditions that large voids provide, then the universe's habitable real estate might be far more limited than previously imagined. Most cosmic regions might be too chaotic, too radiation-rich, or too chemically poor to support the long-term evolution of complex organisms. This realization brings us to perhaps the most profound implications of our cosmic isolation. What our unique address reveals about the fundamental relationship between cosmic structure, physical law, and the emergence of consciousness in the universe. The vast desert that surrounds us might represent more than an accident of cosmic evolution. It might be a necessary condition for complexity itself. Chapter 8. Universal Implications. Our cosmic isolation raises profound questions about the nature of observation itself and our ability to understand the universe from within our unique cosmic address. Every measurement we make, every theory we develop, and every conclusion we draw about cosmic reality emerges from this singular vantage point within an extraordinarily rare cosmic structure. The implications cascade through every branch of astronomy and physics. Consider the fundamental challenge. We have only one observable universe, viewed from one location, at one moment in cosmic history. But that location now appears to be among the most unusual in the cosmos, a discovery that forces us to reconsider whether observations represent cosmic norms or local anomalies. It's as if we've been studying oceanography while standing on a unique island, unaware that the waters around us differ fundamentally from typical oceanic conditions. The cosmological principle, which assumes that the universe looks roughly the same when viewed from any location on sufficiently large scales, suddenly requires careful re-examination. Our void's existence suggests that cosmic homogeneity might break down on scales smaller than the 300 million light-years that cosmologists traditionally considered sufficiently large. If cosmic structure varies dramatically on billion light-year scales, then many of our fundamental assumptions about universal properties need revision. Dr. Sabir Sarkar from Oxford University has argued that recognizing our void location requires rebuilding cosmology from first principles. We've constructed our understanding of dark energy, cosmic expansion, and even the Big Bang itself using observations that might be systematically biased by our unusual cosmic address, Sarkar explains. Every cosmological measurement we've ever made needs reanalysis in light of this discovery. The implications extend to our understanding of dark energy, the mysterious force driving cosmic acceleration. Current estimates suggest dark energy comprises 68% of the universe's total energy density, but these calculations rely on expansion measurements taken from within our void, where space expands faster than cosmic averages. If we account for our location bias, the true cosmic proportion of dark energy might be significantly different, perhaps as low as 60% or as high as 75%. This uncertainty propagates through every aspect of cosmological theory. Models of cosmic fate, the universe's ultimate destiny, depend critically on dark energy's exact strength. If dark energy proves stronger than current estimates suggest, the universe might experience accelerating expansion that eventually tears apart galaxies, stars, and even atoms themselves in a Big Rip scenario. If weaker, cosmic expansion might eventually slow, stop, or even reverse into a contracting phase. The discovery also challenges our understanding of cosmic initial conditions. The standard model of cosmic inflation predicts that density fluctuations in the early universe should follow specific, statistical patterns that produce cosmic structure similar to what we observe. But generating a void as large and perfectly positioned as ours requires initial conditions so improbable that they approach the realm of cosmic conspiracy. Dr. Alan Guth, who developed inflation theory, acknowledges the challenge. Voids like yours suggest either that inflation operated differently than we understand, or that we're observing the universe during an exceptionally rare configuration of cosmic structure. Both possibilities require significant theoretical development. Alternative cosmological models attempt to explain our void without invoking extreme improbability. Some propose that the universe is far larger and more complex than we observe, with our observable universe representing only a tiny fraction of a vast cosmic structure where regions like our void occur naturally. Others suggest that cosmic evolution includes processes we haven't yet discovered, perhaps interactions with extra dimensions or influences from parallel universes. The anthropic principle offers another perspective on our cosmic address. This controversial idea suggests that we observe the universe's properties, partly because those properties allow observers like ourselves to exist. If complex life requires the stable conditions that large voids provide, then intelligent observers would naturally find themselves in cosmic locations similar to ours, regardless of how rare such locations might be. Dr. Max Tegmark from MIT has developed mathematical frameworks for analyzing anthropic arguments in cosmology. His calculations suggest that if life requires the galactic stability that void environments provide, Then, observers throughout the cosmos would expect to find themselves in locations similar to ours. This would transform our apparent cosmic isolation from an improbable coincidence into a necessary consequence of our existence. The implications extend beyond cosmology to fundamental physics. If our observations are systematically biased by our void location, then measurements of fundamental constants, particle physics parameters, and even the laws of physics themselves might need recalibration. Constants like the fine structure constant, the gravitational coupling strength, and the electron-to-proton mass ratio might appear different to observers in typical cosmic neighborhoods. Recent theoretical work by Dr. Joe Maggio from Imperial College London explores whether fundamental constants vary across cosmic structure. His model suggests that the reduced matter density within voids might affect the effective strength of fundamental interactions in subtle but measurable ways. If confirmed through precision measurements, this would represent revolutionary evidence for the deep connection between cosmic structure and physical law. The discovery also has profound implications for the search for extraterrestrial life. If complex biological evolution requires the stable conditions that void environments provide, then the cosmic distribution of life might be far more restricted than optimistic estimates suggest. Most of the universe's volume exists in dense cosmic regions where the chaotic gravitational environment might preclude the long-term stellar and planetary stability necessary for complex life. This possibility dramatically reduces estimates of cosmic habitability. Rather than life emerging throughout the universe, wherever basic chemical and physical conditions are met, complex life might be confined to the rare void environments that provide billions of years of stable evolution. The famous Fermi paradox, the apparent absence of detectable alien civilizations, despite the universe's vast size and age, might find resolution in cosmic geography rather than biology or physics. Dr. Milan Hrkovic from the Serbian Academy of Sciences has calculated that if life requires void environments like ours, the number of potential civilizations in the observable universe drops by factors of thousands or millions compared to traditional estimates. This would explain why SETI searches have found no evidence for alien intelligence while maintaining optimism about life's eventual discovery in similar cosmic environments. The philosophical implications prove equally profound. Our cosmic address forces us to confront fundamental questions about objectivity, observation, and our ability to understand reality from within it. If every measurement we make is influenced by our unique location, how can we distinguish universal truths from local phenomena? The problem resembles trying to understand climate while living in a unique microenvironment that differs from global norms. This observational challenge extends to consciousness itself. If awareness emerges only under the specific conditions that void environments provide, then consciousness might be far rarer in the cosmos than we imagine. The universe might be filled with simple life forms, but nearly devoid of the complex nervous systems capable of scientific observation and philosophical reflection. Understanding these universal implications requires developing new theoretical frameworks that account for observer bias on cosmic scales. We need methods for distinguishing local phenomena from universal principles, techniques for correcting observational biases caused by our unusual location, and theories that can predict what the universe would look like from other cosmic addresses. The challenge is both scientific and philosophical. Science progresses through observations that test theoretical predictions, but if our observations are systematically biased by our cosmic location, then the entire scientific enterprise requires recalibration. We must learn to think beyond our local perspective while acknowledging that every observation emerges from our unique cosmic context. Perhaps most remarkably, our void's existence suggests deep connections between cosmic structure, physical law, and the emergence of consciousness that we're only beginning to explore. The vast emptiness that surrounds us might represent more than an accident of cosmic evolution. It might be a necessary condition for the universe to become aware of itself through observers like us. This brings us to the most profound question of all. What does our cosmic isolation reveal about the ultimate destiny of consciousness in an expanding, evolving universe?